Swayam Prabha. Digital India. Educated India.
Welcome to another problem solving session. In this segment we'll be continuing what we were doing in the previous segment. So if you recall, what we were doing is we were computing the Lagrange multiplier. So we computed what beta was, and there is another Lagrange multiplier which is alpha. That is what we will be doing now. Okay, so let's see. So if you recall again from the classical thermodynamics, so if you see here this equation of the differential of ds, from here we can compute the partial of s with respect to, let's say, n. So partial s partial n at constant energy and volume, let's say, so E and V constant, so that becomes minus mu over T. Okay, so we will be using this thing later to evaluate our second Lagrange multiplier. As we saw, we already used this expression to compute the first Lagrange multiplier, which was the beta actually. So now we will be computing alpha, and this expression will help us to do. So what we will do is, so we know the right hand side of this partial s partial n from classical thermo, and from statistical thermodynamics we will be able to compute this left hand side of this expression. So let's compute partial s partial n just like before, where all these things will exactly remain the same, just we will be differentiating with respect to n now. Okay, so if we do that, what we'll have is partial s partial n at constant E and V. So E comma V is constant. This is K times the energy times partial beta partial n, okay, at constant E and V, plus K times alpha plus K times n partial alpha partial n at constant E comma V, minus the Boltzmann's constant, sum over J in J bracket partial alpha partial n at constant E and V, plus epsilon j partial b partial n at E and V. Okay, so if you see the expression for s, we'll be able to see exactly how this came. So what we did was we differentiated now with respect to n. So here we and again we need to remember that alpha and beta is a function of n here. Okay, so what we did here was Ke times partial beta partial n. So that is Ke, that's constant, because remember this is the Boltzmann constant and this is the total energy which is constant, multiplied by partial b partial n, plus, and now this we need to differentiate with respect to n, and you see alpha is also a function of n, so that means you have to use the product rule, and hence we will have two terms. So these terms, k alpha plus k n partial alpha partial n, minus k and sum over j, and we had this term, remember, and this term we later realized was the equilibrium particle distribution, which is nj. Okay, and this multiplied, if you see, this was multiplied by the derivative of alphas and betas, so it says partial alpha partial, but now we are doing with respect to n, and then epsilon g partial beta partial n. Okay, so that's this expression. And now if you just open the brackets, we'll be seeing what this will become is, recognize again that sum over j and j is the total n, and sum over j and j epsilon j is the total energy. If you see, if you open the bracket, so this kn, this will become kn partial alpha partial n ev, that will cancel out this term, and then we will have minus ke partial beta partial n ev, that will cancel this first term. So what will be left is partial s partial with respect to n at constant e comma v is given by k times alpha. And from classical thermodynamics we know that this is equal to minus mu over t. So from here we computed the second Lagrange multiplier, which is alpha equals minus mu by kt. Okay, so that's the generic method of finding the Lagrange multiplier in case of Bose-Einstein and Fermi-Dirac statistics, given when we started with the entropy. This could be done, by the way, for any other macroscopic thermodynamic variable, like for example the Helmholtz function, the internal energy, the Gibbs free energy. Okay, but the methodology remains more or less the same. Okay, one of the key important thing that we need to realize here is this thing that alpha and beta, that the Lagrange multipliers are functions of e, v, and n, and hence when we are doing the partial derivatives we need to differentiate alphas and betas with respect to the individual variables. Okay, so let's say now we move on to the next part of this discussion, where we are so we now know alphas and betas, and now the question is, can we find out a general expression for pressure? Okay, so compute P, okay, in terms of entropy basically. Okay, so we can write that from classical thermodynamics, but what we need to write is, so this we can write, we know from classical thermodynamics, we know the physical picture behind it, but we need to find out so we want to write P is the pressure in terms of the particle distribution Nj, the energy states epsilon j. Okay, so the thing that we need to that we want to write now. Okay, so if you remember the differential for ds, that itself we can define the pressure. So you see the partial s with respect to v gives us p over t. Okay, at constant at constant e and n. So that means we have the partial of the entropy with respect to v at constant e and n, that is equal to p over t. Okay, and that means let's do the same thing. We know the entropy, and now we will differentiate with respect to v. Okay, and again realize that alphas and betas the function of v. Okay, so this expression will become partial s partial v of e comma n, and this will become equal to k times e partial beta partial v e comma n plus k n partial alpha partial v e comma n minus k sum over j and j times the bracketed term. So if you remember, where is this bracketed term coming from? So if you see, this is where the bracketed term is coming from. But now what we need to realize is that since we are differentiating with respect to volume now, so epsilon j, the energy, is also a function of volume. So that means we will have to differentiate with the we will have three terms of alpha, beta, and epsilon j. So here we will be using the product rule basically. So everything remains the same, just we will have an additional term here. Okay, because epsilon j is a function of, that is the total size of the system that we are dealing with. Okay, so this becomes minus k sum over j and j partial alpha partial v e comma n plus epsilon j partial beta partial v e comma n and then the product rule second term, which is now we keep beta constant, and then we differentiate epsilon j with respect to v at e comma n. Okay, so that's the expression for partial s partial v. Okay, and if you see this again using the same ideas before, that sum over nj is n and sum over nj epsilon j is e, this expression becomes, so you will see this is kn, this will become kn, and this will cancel this term, and then we will have ke partial b partial v, that will cancel this first term. So what we'll be left with is this extra term which we just had now. So we'll have partial s partial v e comma n, and that is minus k sum over j nj partial epsilon j partial v e comma n. Okay, and if you realize, this is what from classical, this was p by t. Okay, so and so if you look at this expression, we know what beta is, that we evaluated, that was a Lagrange multiplier also. Beta was 1 over kt. So if beta is, so that is beta is 1 over kt, that means k times beta is 1 over t, so this expression becomes 1 minus 1 over t sum over j and j partial epsilon j partial v with respect to e comma n, and that is equal to p over t, and this becomes therefore the pressure. So the pressure can be written as p equals minus sum over j and j partial epsilon j partial v at constant e and n. Okay, so that's the expression of pressure from a statistical thermodynamics point of view. Okay, in terms of, you see, the energy states epsilon j, and in terms of the particle distribution in j. Okay, so here we use this important fact about the particle distribution nj, and this we derived in the main lectures. If you see, if you refer to the main lectures, you will see how this nj was derived, and it was derived from the statistical probability, and then finding the stationary points of that probability distribution. Okay, so now we will try to do something similar, that is, we'll try to find out the equilibrium particle density, but not for Bose-Einstein or Fermi-Dirac statistics. But so the problem that we are trying to do currently is trying to find out the thermodynamic, or let's say, let's write the question. So the thermodynamic, this is the question, thermodynamic probability for classical Maxwell-Boltzmann statistics WMB, and that is given, that is n factorial times the product over j gj power nj divided by nj factorial. Okay, and here what we mean by classical Maxwell-Boltzmann statistics is the statistics that was derived by Boltzmann himself, and he assumed the particles to be distinguishable okay, and no limits on the number of particles in each energy state, okay, where we recall Nj is the number of particles in the jth energy state, so this is the number of particles, and Gj is the degeneracy of the jth energy level. And the question is, what we need to find out is the equilibrium particle distribution. That is, you want to find out what is Nj, okay, equilibrium particle distribution. So that's the question that we want to tackle. Okay, so this kind of statistics is, you can think about an example of this in more practical sense. So a solid that is composed of localized atoms at distinguishable lattice sites. So that's a practical example of where the statistics could be handy. Okay, so let's try to find out this equilibrium particle distribution for the classical Boltzmann statistics. Okay, so given that the thermodynamic probability for the Maxwell-Boltzmann statistics, the classical version of it is n factorial, the product of j gj power nj divided by nj factorial. Okay, let's take the log of both sides, the log of mb, and this becomes log of n factorial product of j gj nj over nj factorial. Okay, and this, by using the properties of the logarithm function, can be written as log factorial plus log of the product of j gj nj by nj factorial. Okay, so this could be again simplified further. The logarithm of the Boltzmann probability is log n factorial plus, now you see this is log of a product, and log of a product converts it into a sum, so this becomes a sum over j, and that becomes nj log gj, so that is coming from this term, log of that term, minus, this is in the denominator, so minus log nj factorial. Okay, and now let's say if we use the Stirling's approximation, which says the log of n factorial is approximately equal to n log n minus n for n tends to infinity, for very large n. Okay. Technically it should be, since it's countable, it's greater than 1. Okay, so if we use this Stirling's approximation in this equation, this becomes log of WMB, and this becomes n log n minus n. Okay, so n log n minus n plus sum over j nj log gj minus nj log nj plus nj, where we use Stirling's approximation here and here both. Okay, so if you see that, let's recall the constraints. The constraint is sum over j, and j is n, and sum over j epsilon j and j is e. So if we want to find the stationary positions for this function, what we need to do is take the differential of that and equate to 0. So we want d log wmb. You want to maximize that thing, that will become sum over j. Let's do this term first. So this becomes different, so we will differentiate with respect to nj itself. So this will become log gj minus log nj minus 1 dnj. Okay, where we recall, so if we differentiate the constraints themselves, so this will become sum over j dnj equals 0, and sum over j epsilon j dnj equals 0. So now if we use the method of Lagrange multipliers, which we discussed in the previous segments, this will become sum over j log gj by nj, that is coming from this term, minus the first Lagrange multiplier times the constraint, which is sum over dnj, but that we will write. So let me write it like this. So this is dnj, so that's the first Lagrange multiplier times the second, so minus beta epsilon j, so that's the second Lagrange multiplier. So this should be equal to 0. Okay, if this has to be equal to 0 for arbitrary variations of dnj, that means this entire thing has to be 0. Okay, so therefore we have log of gj by nj equals alpha plus beta epsilon j, and hence from here we can write nj equals gj e to the power minus alpha e to the power minus beta epsilon j. That's the equilibrium particle distribution for classical Boltzmann statistics. Okay, that's how we do it for any general statistics. So we start with the thermodynamic probability for that statistic, and this comes from the fundamentals of probability theory, permutations and combinations. And once we have this, then what we do is we take the log of that thing and then log of the factorial. Okay, so we have log of factorial, and then we use, basically we want to convert it into some kind of a continuous version for large n's. So what we do is we use the Stirling's approximation, we do it, convert it into a continuous problem, and then we use the method of Lagrange multipliers to optimize the function, the logarithm of the thermodynamic probability under the given constraints, and then we use the method of Lagrange multipliers to compute the equilibrium particle distribution. Okay? And once we know the equilibrium particle distribution, and as it has been discussed in the main lectures, we know the partition function. That is another important concept. So if we know the partition function and nj is basically nj is related to the partition function basically. So in principle, if we know the partition function, we can compute all thermodynamic quantities in general. Okay, so that's for this segment, and we will see you in the next segment. Thank you.